Hi guys, last time we were talking about the first fundamental theorem of calculus, and as a quick review, try to remember what the heck that stated. I'll give you a second. Maybe pause the video and give it a shot. All right, well, the first fundamental theorem of calculus said that if f of x is continuous on the interval a to b, and the derivative of big of f of x is equal to little f of x, then the integral from a to b of f of x dx is equal to big F of b minus big F of a. Well, the power in this, once again, was that this is actually just notation for something which is way more complicated, namely the limit as n goes to infinity of the sum I goes from 1 to n of f of x of I delta x. In other words, this symbol or this notation is used to describe this process. What process am I talking about? I'm talking about a process where we divide our interval into n subintervals. So here I'm breaking it into 2 subintervals. And I'm taking f of x of I, that's the height, times delta x for that guy, and for this guy, and I'm adding them up. So I do it for 2 rectangles, n rectangles, more and more rectangles, take the limit as n goes to infinity, and that will give me the area under this thing. So this is represented by this, and this equals this. So again, why is that important? That's important because this is really way easier to compute this way. So instead of having to do this limit, we can just play this game. So as a quick example, let's say we want the integral from 0 to 1 of x dx. And again, graphically, what we're doing is we're finding the area under this guy from 0 to 1. Of course, for this particular example, you could use the triangle formula, but let's do it using calculus. So by FTOC part 1, this is x squared over 2, because the derivative of x squared over 2 is just x. And evaluating that from 0 to 1, we get 1 squared over 2 minus 0 squared over 2, or a half. Okay, so hopefully you realize that this is a very powerful tool, powerful method by which we can compute these integrals. So now that we have a way of computing this guy, I want to take a step back and learn a little bit more about this in general. So in other words, today what we're going to do is we're going to study the properties of this thing. And when you study mathematical properties, sometimes you find out sometime down the line that knowing about the particular property makes further computations easier. So that's why we're going to do that. So today's lecture then is about properties of the integral. So the first property that I want to talk about is that the integral from a to b of f of x dx is equal to minus the integral from b to a of f of x dx. So let me point something out first. If you look here, up until now we've been saying to ourselves, this is representing an area. So I think it would be natural if a were less than b. So we're going from a to b. But now I'm saying, well, wait a minute, there's nothing precluding us from switching these guys so that the bigger number is down here, potentially, and a smaller number up there. And what I'm saying here is that this integral has this relationship with this other guy. So how do we prove that? So first off, let me say that in this course, I don't expect you guys to prove anything, but proofs are always helpful because they give us confidence in formulas that we're using. They turn out to not be these mysterious black boxes. And a lot of times along the way, we pick up additional information or insight that we wouldn't have known beforehand. So the way I'm going to prove this is proof by algebra, or proof by just writing it down. So we know by FTOC Part 1, the Fundamental Theorem of Calculus Part 1, that this is the same thing as big F of B minus big F of A. And actually, I should be a little bit careful here. We're going to assume in all of these that f of x is continuous. So I need to actually state that because in the first fundamental theorem of calculus theorem, we're assuming that f of x is a continuous function. All right, so my goal is to turn this guy somehow into this guy. So I'd like to invite you to pause the video for a second and see if you can somehow manipulate this into this. All right, let's see how to do it. Well, this is the same thing as minus f of b plus f of a. So in other words, all I'm doing is factoring out a negative. But if that's the case, then I can rewrite it as big F of a minus big F of b. Because addition is commutative. That means that we can reorder things. Now, I'm just going to use the first fundamental theorem of calculus, but going backwards. So this is the same thing as minus the integral from, well, let's see. Looks like I'm going from b to a, little f of x dx. And that's why that's true. All right. So that's the end of that proof. This is a formula which, again, hey, maybe it'll be helpful, maybe it won't be helpful. We don't know, but it's something that we've derived, and later on we'll see about potential uses. All right, so that's the first property. The second property that I want to talk about is that the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So I'm going from a to c of f of x dx and from c to b of f of x dx equals, well, before I tell you the punchline and before we prove it, let's draw a picture to maybe see if we can figure out what the punchline is. So I'm going to draw a picture. And I do have to say there's no assumption that f of x is above the x-axis. So this isn't going to be a proof. This is just a way for us to kind of intuit what's going on, and then we'll do an actual proof. So I'm going to make an assumption that a is less than c and c is less than b. But I have to be clear about this. What we're going to prove does not depend on this relationship. So b could be the smallest number, c could be the largest number, but I'm just looking at one particular case, and mathematicians do this a lot. They look at one case just to try and get a sense as to what's going on. Well, from a to c, that integral is literally going to be this area. From c to b, that integral is literally going to be this area. So I'm going to give you a minute. I want you to pause the video and see what you think this integral is equal to. All right, hopefully you said that's the same thing as the integral from going from a to b of f of x dx. So that's the property. Again, I didn't actually prove that statement. I hopefully convinced you in this super special case that c is in the middle, a is the smallest, b is the largest, and f of x happens to be positive. But I'd like to prove this in general. And to do that, I'm once again going to use the first fundamental theorem of calculus. So let me erase this. And let's do the proof. And from now on, I'm going to write PF for proof. And to prove it, I'll play the same game. Let me write this out. And my goal is to somehow get this. Well, by the first fundamental theorem of calculus, part 1, this guy is big F of c minus big F minus big F of A, right? This is big F of C minus big F of A. Plus, this guy is big F of B minus big F of C. Now I want you to take a look here. Can you see what cancels out? Yeah, big F of C goes away, this goes away, and I can rewrite this as big F of B minus big F of A. Again, fundamental theorem of calculus backwards, this is the same thing as the integral from A to B of f of x dx. So that's another property of integrals. All right, as yet another property of integrals, the integral from A to B of f of x plus g of x dx equals, well, let's see, we're taking the integral of a sum here, the integral of a sum. And integrals are going in the opposite direction of derivatives. And we know that the derivative of a sum of two things is the sum of the individual derivatives from a previous calculus course. So I wouldn't be surprised if this is equal to this. In other words, the integral of a sum of two functions is the sum of the two integrals. So that's not a proof at all. But this is what I think I wouldn't be surprised if it's this because it worked with derivatives. And again, this is the opposite process. It turns out this is a true statement, and let's actually prove it. Again, though, I guess I want to highlight the point that mathematicians, they ask themselves, hey, if you're trying to prove something and you don't know a result, you intuit or think, what could it possibly be before you actually do the proof. So let's prove this. So prove this integral well, by FTOC part 1, that's just going to be big F of x plus big G of x evaluated from A to B. Why is that? Sorry, it should be a big G of x. So what I'm doing is I'm saying the derivative of this guy is this guy, the derivative of this guy is this guy. So we know that that's true because, again, the derivative of a sum is the sum of the derivatives. So hopefully you agree that if I have two functions here and I add them, and the derivative of this guy is this guy, the derivative of this guy is this guy, then the derivative of the sum of that guy will be that guy. So this is the function that we need for FTOC part 1. Well, we then get that big F of B plus big G of B, so I'm just plugging in, minus big F of A plus big G of A is equal to the same thing as big F of B minus big F of A, so that's this minus this, plus big G of B minus big G of A. Can you guys see the punchline? This is the integral from A to B of f of x dx. And this guy is the integral from A to B of g of x dx. So that means that if we want to integrate something, we can just break it apart into smaller pieces and do it term by term. And let me also say that addition and subtraction work the same exact way in terms of differentiating. So they work actually the same exact way in terms of integrating as well. So this is true if I'm adding or subtracting two functions. So the details in here might be a little bit different in terms of the proof. You might have to switch the signs in here. But the bottom line is that if you subtract functions within an integral, you can do them separately. All right, so that's another property of integrals. about this one? The integral from a to b of c times f of x dx equals. All right, so once again, let me try to intuit my right-hand side, and then I'll prove it. Let me draw a picture, see what's going on. Again, just to make life easier for myself, I'm going to assume that a is less than b. I'm going to assume that f of x is positive, but there's no reason for f of x to be positive in this statement or for this relationship to hold. I'm doing a special case so that I can try to see what's going on. Well, that integral is giving me this area. And c times f of x is multiplying all of the y values here by c. So it's stretching this guy up. Well, if this, without the c, gives me this area, what do you think is going to happen if I multiply the function by c? So hopefully you said, well, that's just going to multiply the entire area by the c value. So in other words, it looks like we can just pull that c out of the integral sign. And it turns out that that is a true statement. So here's the proof. Well, once again, let me start here. And actually, for this one, I'm going to invite you to pause the video and see if you can complete the proof yourself, and then press play. Okay, so hopefully you said that this is the same thing as c times big F of x, right? Because when you take the derivative of this guy, the constant goes along to the right. This is then c times big F of b minus c times big F of a. Well, what can we do algebraically here? Looks like I can pull out that c, and then can you see the punchline? This is just the integral from a to b of f of x dx. So that's why this is true. All right, we have a couple more properties to know. The integral from a to a of f of x dx. Well, I'm going to give you a minute. Think about this. What do you think that integral is going to be? Draw a picture in terms of what's going on, and then press play again on the video. So hopefully you have this interesting picture where I'm trying to find this area from a to a. And that area is just 0. So let's see a formal proof of that. Well, the integral from a to a of f of x dx is big F of x evaluated from a to a. So it's big F of a minus big F of a, or 0. So that's why that's true. This might seem like a useless property, or I don't know, maybe you think all these properties are useless, but it turns out that a bunch of these, even this one, is going to pop up in a future lecture as something useful to know. All right, we have a couple more properties. So let's see. If f of x is odd, then the integral from minus a to a of little f of x is 0. So first off, what is an odd function? What is an odd function? So odd here doesn't mean different. Odd has a very definite meaning. And there's an algebraic definition of being odd. And there's also a graphical one. So let me do the graphical one first so we can see what's going on. So a function is odd. So for example, x cubed, that's an odd function, if it can be reflected through the origin. So the way that I think about this is if I take a quarter of the function and I flip it over this way, and I flip it over this way, and then I flip it over this way, so I flip it down, then I get the other part of the function. And that's the case here. So f of x equals x cubed is an odd function. So that would be an example of it. So the formal definition, or I guess the algebraic definition, is that f of x, so this guy here, is the same thing as the opposite of f of negative x. So what that means is as follows. F of negative x flips it this way. So f of x isn't the same as f of negative x. It's actually the opposite of that. So we then flip it over. So why is this true? Well, there are a couple of ways you could think about it. Again, with the intuition, if I'm going from minus a to a, then hopefully you can see that we have the same amount of stuff on both sides there. Because we have the same amount of stuff, and this guy's positive and this guy's negative, the integral is going to be 0. So there's another way to prove this, but we actually don't have the tools to prove it the other way. So I'm just going to prove this using this visual example. And finally, the last property is as follows. If f of x is even, then the integral from minus a to a of f of x dx is equal to twice the integral from 0 to a of f of x dx. So this one also we're going to prove by just looking at a picture. It's not a formal proof, but I think it shows us what's going on. So as a reminder, an example of an even function would be f of x equals x squared. And this guy is even because it's got symmetry this way. Okay, symmetry over the y-axis. The formal definition of an even function is that f of x is exactly equal to f of negative x. So whether I stick an x in or negative x in, I get the same y value. So let's see why this is true. Again, we're looking at a picture, not a formal proof, but based on the tools that we have now, this will take us to where we need to be. So I'm going from minus a to a. So hopefully you can see by the symmetry that I can either integrate from here to here, or I could take twice this area. In other words, going from 0 to a. So those are the properties of the integrals, and we did go through a whole bunch of them, so I want to highlight them or summarize them really quickly on the board for you guys to have. And I would suggest writing these down, maybe put them on index cards so that you can remember them. So the integral from a to b of f of x dx was negative the integral from b to a of f of x dx. So again, the idea is that if you switch the order of integration, you have to flip the sign here. Second, we talked about the fact that the integral from a to c of f of x dx plus the integral from c to b of f of x dx is the same thing as the integral from a to b of f of x dx. And we proved this formally, and I said, hey, it doesn't matter what the order of a, b, and c are, but I think this makes sense visually. If we do consider the case where the order is a, c, b, again, I just drew a picture, and I took the area from here to here, plus the area from here to here. It's the same thing as the area from the start to the finish. We then also proved that the integral from a to b of f of x plus or minus g of x dx is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. In other words, if you have a complicated function here and you need to integrate it, you can just break it up into the smaller pieces and deal with them piecewise. We also said that the integral from a to b of c times f of x dx is equal to c times the integral from a to b of f of x dx. In other words, we can just pull the constants out. We also said that the integral from a to a of f of x dx was equal to 0. So the visual interpretation of this is that the area of a single point up to the function is going to be 0. And then we prove that f of x is odd. Then the integral from minus a to a of f of x dx is 0. Finally, f of x is even. We said that the integral from minus a to a of f of x dx is twice the integral from 0 to a of f of x dx. So those are all the properties of integrals that I want you guys to be familiar with. And if you have any questions, feel free to get in touch. Thanks so much.